Okay, hello. Oh, 20 people watching? Wait, what are you guys doing here? Hello, everybody. So, this is a new day of implementing porting the AC implementation of a Radix tree to Zig. We're implementing removal. I think that after we have removal, we'll have pretty much everything that I care about. Because there would still be search that would need to be implemented. But I don't need the search in the sense that, well, if we wanted to have this implementation be, a full replacement for the original, then yeah, we would want to do that. But I don't care about that. I'm looking at this more from a learning perspective. I'm using it to test drive an abstraction that I've implemented called ZigFlex. So that's what we're doing more than anything else. Still. Okay, so this is what we're working on. Give me a bit of time to, do the announcements and then get something to drink. And then we can start. Okay, I'm gonna go get something to drink and then we can start. I'll be right back. Okay. So, what was I doing? Yesterday I got more or less. I've implemented the first few lines of fetch remove, the first case here, and their Teufel. Their Teufel. I have a vague memory of somebody named their Teufel. It's been so long, I don't remember. By the way, are you coming to Zigtoberfest this year? Think you will be able to make it? Okay, so this is the code that we're looking at and that we're porting. So actually, this is it. Okay, it's here where it says if child This is our if child. So here we call Rax remove child. You doubt it. Yeah, I see. Unfortunate. So, well, but I hope that everything else is okay. Okay, we need to remove child. So what we're stating is that child, what we're stating is that child, let's look at what we did just now. If the current node is empty, then while the current node is not root, we assign the current node to child, we call the init, and then we pop one item from the stack. And then we loop again. And with this, we're removing everything up, all the way up to root. All the way up to root. And then basically what happens is that as long as h is different than root, we keep assigning h to child. So, and then we pop. So at the end, we will end up with h. We exit this, we only exit this loop. Well, there's also this one that is a break condition, but we're basically gonna end with either root or a node that has these properties, a node that is a key or that is a split node with more than one children, and well, with more than one byte in it. And so in that case, we break, and then we're doing stuff with child. Wait, there's something sus in here. Don't we the init child? So every time we assign child, we the init child. It should be or. Thank you. Yes, that was that was this. Yeah. There's something sus though. Let me look at this code. Here we're assigning h to child, and then we rax free child every single time we rax free child. So, and then we assign h. But then if we break from here, so here's the thing that I don't understand. What if, I guess there is a, what I'm suspecting might happen will not happen for reasons other than what's immediately written in the code. But the idea is, here, every time we free what we assign to child, and then if we break from this loop, and this condition holds true, then we're gonna try to access a dangling pointer. And that's the part that I find kind of sus. That said, to be fair, we don't know entirely what Rax free does. Oh, it's just a normal free, okay. Right, it's just macro, the macro version of that. So I guess the expectation, you don't access it directly. What does that mean? You do access it directly though. Look at this. This is branching on whether this is a null pointer or a, well, non-null pointer. And so Rax free is not going to be able to modify the pointer in this variable because it doesn't take a pointer to it. So it can't write to this. Although, to be fair, this is a macro, so technically it could if it wanted to. Fucking see. But but in this case, this macro is just like indirection. It's just it's just the normal free. So if we assign something to child and we free it, then there's going to be a bad pointer in here. And so my question is, wait, what if we enter in here, we do this, and then we break from this? Then what happens here? We will have assigned to a child that... Yeah, but then here you will have a dangling pointer. You will have a pointer to memory that you freed. That's the problem. Because we never assign null to it. So the moment that we assign a value to it, yeah, you check the pointer is not null. Then how is this guy going to know that the memory that it's reading is garbage or not? Oh, I guess I understand what you're saying. What you're saying is that this guy then will use this information. We'll use just the pointer to remove it from here without ever dereferencing it. Jesus, yeah, that makes sense. Yeah, you're right. You were right. Let's see. Rax remove child. Low level child removal from node. The new node pointer after the child removal is returned. Note that this function does not fix the pointer of the parent node in its parent, so this task is up to the caller. The function never fails for out of memory. With our current design, unfortunately, we cannot guarantee that. Oof. So if the parent is compressed, does something to it, and then let's see, while true. Let's see, to start, we seek the first element in both the student point and an edge bytes in the node. Wait, what? Let's see. If the parent is a compressed node having a single child as per definition of the data structure, the removal of the child consists into turning it into a normal node without children. Wait, does Rax get data like applies the defects? No. Oh, and then we do set data. Okay, now I get it. We do get data. Okay, let's see what happens. If the parent node is compressed, then we copy its data. We make it a split node, an empty split node, and we reapply the data. What am I missing? Wait a second. Why are we doing this? Okay. Is it me, or is there something fishy in what we're looking at? It's so data is a pointer. It's setting size to 0. But I really don't get why are we copying this and then setting it back? And again, this seems to make sense only if this guy is causing a some kind of side effect, but it's not really. It's just copying the data out. Hello, Ender Zombie. Why are we doing this and then this? This seems super weird. Get data, set data, use the size for the offset. Oh, great point. Yes, you're right. So yeah, right. That is the whole point. Thank you. The whole point is that we are basically applying. We are doing a memory resize, but without. So we're like shrinking the node, but we're not reallocating. But we're not reallocating the node. We are letting the node be bigger than that. That seems in some ways good, in some ways bad. In some ways, it seems good. In some ways, it seems bad. So here's the problem. Right now, with my current design, I'm unable to allow the memory allocation to go out of sync with the size counting that we're doing. We can't lie about the size in the struct. And the C code is able to, though, mainly for one reason, because the C code uses an allocator that doesn't care about you providing length information for an allocation. So in C, you can just give you can just free a pointer without knowing how big is that allocation. In Zig, it doesn't work that way. In Zig, the expectation is that the allocator interface requires you to also pass length information, which is actually not a bad idea in some, at least in some ways, because, for example, in debug mode, you can catch whenever you're doing wrong stuff with memory, because you're like, you can get a panic that tells you, look, you were thinking that you were freeing a allocation of length 5, you're actually freeing an allocation of length 10, for example. So you're thinking wrong. But that means that if we want to be able to get the internal state and if you wanted to get the internal state and the actual memory allocation to go out of sync, then we would need an extra parameter that contains the whole length, like the full length. So either we make this a fallible operation. No, you know what? Never mind. This is not a problem. No, I think it is a problem because the allocator can refuse to resize our allocation. There is a we don't have to remap, we don't have to realloc. We can just choose to use resize. The problem is the resize, when it can't, it will just say no. It will not do it for us. It will just say no. So we will need to keep around information about any potential slack. This could be one way of solving it. Having a Slack field where we keep information about any potential Slack. And frankly, I actually did want to gain that ability. I wanted to have the API support this. So I'm thinking right now if this is a good moment to take a break from implementing this and add this extra capability to our system. And I'm thinking we should. I'm thinking we should. Hmm. So let's see how that would look like. I think it would look like something like this, probably layout. Then we could have Slack. And Slack could be so layout is a U1. Then we have a boolean for value. And then we have 30 bytes for bytes. And maybe we could lower this. Okay, Google is not being helpful. Yeah, I don't know. That's a lot. U15. How much is this? 32K. Is this Zig language? It is, yes. So here's my question. How big should a individual node in the Radix tree be allowed to be? Frankly, having 32 kilobyte nodes is not a bad idea. Like, are you going to put into the Radix tree gigantic, like ginormous strings? Maybe not. Probably not. So what we could do. U20 is 1 megabyte, and U10. 1 kilobyte. Not a lot, huh? Is this a website generator or what? Zine here in this website. This is a static site generator. But right now I'm working on a Radix implementation. This is a data structure. I would probably assume max path length strings. Well, you don't only put paths in a Radix tree. You can put also other things. That said, this is not gonna be the maximum limit of an entry that you can put in the Radix tree. That is unbounded. This is gonna be the maximum room in one single node. So you are gonna have multiple nodes. But like if you have a very long string, then it's gonna become like 2, 3, 4, 5 different nodes in a row. I'm thinking of doing it this way. U15, it's going to be U15 of maximum size and U15 of maximum length. But that is dumb, right? Because it shouldn't be this way. I think it should be like a 2-to-1 ratio, I think. It's a 2-to-1 ratio. I think it should be U20 and U10. Okay, let me do it this way. I think we have some weird human readable numbers. I think it's an FMT. Yeah, does anybody remember? Oh, there we go. Parse inside suffix. No, there's some kind of like print size. I'm pretty sure we have it. Some kind of print size that prints the number in a nice way. Does anybody remember how to access this stuff? Options, precision, width, alignment, field. No, come on. I swear there is something like this in the standard library. I think I saw it. Oh, you know what? I think we use it in Zine. With normal print. Oh, B or BI. Thank you. Yeah, so this is wrong because with this setup, the one below is maximum 1 megabyte, the one above is maximum 1 kilobyte. This is definitely not enough. So it can be 15, 15. Maybe this should be 17. Maybe this is what I'm looking for. This is 17 and this is 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. 13. Oh, you know what? No, we want one byte difference. I think that's what we're looking for. I think that's what we're looking for. Let's do 16, 14. $65K, 16K. Yeah, no, it's 1 byte difference that we want. I guess we throw away 1 byte then. So we make this 15 and that 14. Yeah. Is this it? Maybe this should be it. But then we're throwing away 1 byte. Sorry, 1 bit. What do we do with that 1 bit? Where do we put it? I guess we can go back to 1515, which seems weird, but maybe this is it. Fuck it, 1515. 1515 is it. Hello, X2. Okay, we're adding slack then. And we're placing it above here. And it has to be a type that we put ourselves. And this slack is U15, we said. And this we make a U15. And then we need to create slack. You know what? This should be flex.array. So here's the idea. The presence of a slack field means that we store in the slack field the total length. No, sorry, not the total length. We write in it. Would it be nice to put slack after bytes? No, because you have to do math. Also, it has a weird alignment. Well, I guess the question more than anything else is, should it go before or after available? No, this right now is not a packed struct, but this is supposed to be a packed struct. So don't worry about it. This is supposed to be a 32-bit packed struct. Right now it's not because there's a bug in the compiler. So, okay, here's the idea. We have a slack field. In the metaprogramming, we keep notice that we have a slack field. And we use it for nonlinear growth when necessary and for nonlinear growth when necessary and for shrinking, for non-reallocating shrinking. I am starting to think, though, that now that we have all this weird stuff, maybe this would be better if we, instead of having slack, we had tail. And in tail, we have flex.tail. And tail contains this. I don't know how I did this. Um, yeah, let me go here so that we can remove the compiler error. What's going on? Statement pub. Okay, we fucked up. We fucked something else up. What's going on here? So node struct. This is this. This is that. This is that. But we don't want to close node, right? That's it. Okay. And here we can say like true if you want Slack. And that means that we can do this. Well, it would need to also to take this. And then we could do this. Maybe the tail approach is good. And so here's what the tail can do. The tail can add a field that you don't see here that keeps track of Slack. Here's the problem though. We would want to decide how big the Slack should be. And right now we're not choosing, and we should. And it's kind of problematic. Also, you know what I just said about not needing not needing stuff? Well, no, actually, we might actually need stuff. I think that with this architecture, you can delete field names because what you can do is not return this type, but you return another type where you look at these you look at these invocations and you make new ones basically. Or rather, you know what? Maybe you can even make this a tuple, I guess, instead of a struct definition. So, in any case, you can make it happen. This is definitely one approach. I do not like the nesting, though. It really detracts from your ability to understand what's going on. Maybe as ugly as it is, having an explicit Slack here helps. I think for now we should keep it like this. Okay, let's rename flexible array to just array, and let's implement Slack. Man, this is gonna be some work, so let's get ready. So flexible array, I can just, I think I'm better rename it. There we go. Okay, we have array. We need Slack. Hmm. I think that for now we can, this can be actually pretty easy. So with Slack, we return a, oh yeah, I was saying that I wanted to return a, I just wanted to return an int, but it's not as simple as that, because if we just return an int, then we lose information that is the Slack. You know what? Maybe Slack doesn't even need to be a concept that we have in here. Let me think about it for a moment. Maybe we can have separate functions that just know informally that something is a Slack. Yeah, you know what? I don't think we need a Slack. Let's work on the assumption that we don't, and let's implement shrink. So the idea is that we have resize. Let's say that we have also shrink, specialized version of resize. So shrink returns what? Void. Maybe this should be like shrink in place. So I'm just implementing the concept as we see it in Rax. The idea is that we're shrinking an allocation and we are guaranteeing that it will succeed. Oh, right. But the problem is now everything else will break because resize and destroy need to know what the total length is, and to know what the total length is, they need to be they need to be slack aware. They need to know that there is also potentially some slack. So how do we do it? How do we do it? I guess it would be this parameter and this parameter. There is already the concept of some information that they don't have, and then you have to pass anyway. So we might as well do it that way. But at the same time, I'm still deciding if we want to have a shrink type, sorry, a slack type or not. So if we have a slack type, then um, with a slack type, we could pick it up automatically everywhere and reason about it. Otherwise, you would have to pass it manually. Now that I think about it, we don't even, you know what? There's also another completely different approach to this. We don't really necessarily have to do this, I think. So here's how we could do it. Let's imagine, let's like make a table basically. This is like used bytes, and then you have allocated bytes. And then you say, well, okay, use bytes is 0, then allocate bytes is 0. I have one use byte, and then allocated bytes becomes 2. Then I have 2 use bytes, and then allocated bytes stays 2. Then we have 3 allocated bytes, 3 use bytes, and then allocation becomes 8. should we go maybe to 4 first? Let's go to 4. Okay, so we have 4, and this stays 4. Then we go to 5, and then it goes to 8. And it's gonna go to 8 up until we fill it. So my point is, if you define this relationship like beforehand, then you don't need to track how much memory we have allocated, because you can make that a function of the use bytes, right? You know that if a struct has length 3, then length 3 means that the allocated bytes are 4. Although then if from 3 you want to go to 2, then you need to shrink this to 2. Otherwise, your math is not going to work. That said, it's funny because you can then, what you can encode is not really the extra bytes. You encode the power of 2. You're going to go to. And you stop at 32 kilobytes. That said, this does imply wasting some memory. Although, it doesn't necessarily have to be a ton of memory. This is really interesting. You can get definitely cleverer than what I was thinking with this stuff. Especially if what you write down is the power of 2 that you are allocating instead of an offset. And if you're writing down the power of 2, you actually need very few bits. Isn't kind of how release grows? Yeah. That's the same principle. Because that is some behavior, type of behavior they want to put into this Radix 3 implementation. But ArrayList has ArrayList doesn't try to get clever with not storing what the size of the allocation is. This is what I'm trying to achieve here. Not storing how many bytes I'm actually using, but not storing how many bytes are remaining. I think we should make this stuff maybe really everything being a power of 2. And if we make it a power of 2, then we can store, like, we make the allocation always a power of 2. And we store in the Slack, I guess, which power of 2 we're currently at. And if we allow this to go all the way up to 15 to the 15th power, then we only need enough bits to count to 15, which are what, 4 bytes? That said, at that point, maybe we can make it, since we have 32 bits that we can play with, well, actually, does it have to be 32 bits? It doesn't have to be 32 bits. Maybe we could then aim for 16 bits. But let's assume that we stay on 32 bits, then maybe we should rebalance this. And so instead of 15 and 4 bits, then we make it, I don't know. Well, a U5 counts all the way up to 32. And then the other number is not going to be able to go all the way up to 32 already. Out of curiosity, what if we try to aim for 16 bits? What happens then? So if this were to be... Well, for it to be 16 bits, it means that this is 1 bit. This is 2 bits. And so that's already 2 bits. This can be at best 13, but then we need space for the slack. So I guess we can make this 10 and then leaves 3 bits for this guy. Let me do the math. 1 second. 10, 11, 12, 15. Wait, what? 4, 5, 10. Okay, so this can be a U4. It's either that becomes a U4. But now this counts way past, I think, what we need. And this is not really big. How are you finding Zig? I'm trying to learn at the moment by writing a bend code. I don't know what to say bend code. I'm guessing some kind of like bar, QR code, that kind of stuff. Encoder, decoder, but it does involve a bit of metaprogramming comp time that isn't too trivial for the first project. Let me see what's the bend code. Data on the program used by the BitTorrent peer-to-peer file sharing system. Okay, so never mind, something completely different. Understood. Hello, proper bug. So aiming for 16 bits seems a little bit weird because we can only do U10. That is not a lot. U10 means 1 kilobyte. So one node can only contain 1 kilobyte. To be fair, there's a ton of situations where this would actually be fine, you know? There's actually really a ton of situations where this would be perfectly acceptable. 1 kilobyte nodes, good enough. And so you could pull it off. Although, what would the AU4 slack mean? Yeah, wait, there's also this other point. Wait a second. There's also this other point. Why do we need Slack? Why do we need Slack? We don't. So we don't need Slack if we always know that this is gonna, if we always know what the size of this allocation is gonna be. The only thing that would cause us to want to write down that information is this, is this concept, is making this function non-fallible, because then we get that stuff potentially out of sync. And I guess the question is, how out of sync are we getting it? To allow it to be, I don't know, like maximally out of sync, then we would need to be able to say which power. The idea is that we keep trying to be power of 2s in terms of length, always. But then we would have to know when we're going out of sync with that. And so how do you express this? I guess you can express it. Oh, you always are. If you are going to be out of sync, you're going to be out of sync because of deficit. So maybe it could be like a counter, like a delta, where you say Yeah, we are at U10, but actually, um, sorry, max length is U10, and currently we are at I don't know, length I don't know, 8, which is 2 to the third. And so what's happening is that we're basically 7. There's a delta of 7 multiplications by 2. And so we write down 7. And so basically the max value that you need to store is this one. So this means that, let's say 16, again, let's start with 16 bits. So that means 1 bit, 2 bits, 10 bits. So that's 12. So you would need to be able to count up to 12. But 3 bits aren't enough to count up to 12. You would need 4. You don't use all of them, but you need 4. Which you can actually do with this layout. The problem is that the U10 is really miserable. You don't want U10. I think, it's really miserable. So if we go back to 32 bits, then we could make this. Well, this was U30 because it was only 1 and 2. So how many bits do you need to count all the way up to 30? That's 5 bits. 5 bits. It's either, because in terms of bits, it's either 16 or 32. So it's either 4 or 5 bits. So I guess you would want to move this to 26 and then have a 4 bits of slack, basically. This would work. Also, U26 is still like a lot. U26 is. Oh, can we do BI? Let's see what's BI. Yeah, now we're cooking. So it's 64 megabytes. Hmm. 64 megabytes for maximum node size is uh, absolutely reasonable, I think. To be honest, also 10 kilobytes is probably not bad, but okay. So let me think if I'm on board with this plan. So the plan is we assume exponentiation. Here's another question: can we make what if that function was fallible? What if Rax remove child was fallible? What would the consequences be? Because we only do it in here. What if it was fallible? Because here's what I'm thinking. What I'm thinking is that if we somehow are able to make it work with remove child being fallible, and that doesn't cause any trouble, then we don't need to do any size tracking at all. And we can implement the nonlinear growth stuff as we please. Like it's really just the best of all worlds. And at that point, we could very well make a 16-bit header. We don't have to do a 32-bit header at that point at all whatsoever. No need to. So if H is an empty node, we remove it and we go to the parent. And we keep doing it until we find a node that has a key. And from that node, we need to remove one entry. We need to remove one entry from that node. Man, I'm so torn because the ability to shrink a node without fading seems great. The ability to grow non-linearly also seems great. The ability to not have to store total length size seems also super great. But unfortunately, to have all of these things, we need to be able to have that. Hmm. And I mean, the fact that removal should succeed, that is something that we should support. We should allow removal to be something that in general should succeed. So how do we shrink this bad boy in a way that makes sense for us? At that point, the only answer is you add a counter, you had a slack counter. Like there's really no other solution. You either add a slack counter or you don't. Okay, you know what? Enough. I thought about hypotheticals. Enough. Let's have some. Let's do some coding. Let's do some coding. So no slack. This goes to all the way up to U30. Goes back to normal. And then in here we have. Oh yeah, we have this. So we'll think about shrink in the future. For now, let's use the normal APIs. Okay, to compress, if child ch. We're looking at this. If child ch, then we do remove child and then new. Okay, so const new equals r dot. Well, this is not r. This is h dot remove child. And we make this a catch panic to do. Hello, Ready Player Parker. All is well, thank you. Okay, so we need to implement now remove child in Node. The init at split byte merge resize for data function remove child. And actually, this needs GPA. Which is what makes it valuable. Okay, so how does this guy work? We're saying if it's merged, so we switch on end.layout. Merge, we do one thing. Split, we do another. So if it's split, we basically need to reduce it by 1. So we basically need to swap. Okay, let me think about it for a moment. If we just shrink what's in split, we're gonna lose the last element. And what we want is basically to make sure that the last element is this one that we want to say to get rid of. So in a sense, I think it works like this. If the last element is not child, then we need to look at all the other elements, find the one that is child, right there, the last element, we override it basically, and then we shrink. So something like this. I'm curious to see if Antires has a cleverer way of doing this, but we can attempt our initial solution in the meantime. So if node.ptrs.slice might save this, might keep this around at this point. If ptrs at ptrs.len -1 is different than child, then we have to do stuff. Or we could structure it if it's the same, and then we continue, or we break. But we don't have a nice break, so let's do the different case. Nesting, but it's fine. So if the last one is not child, then we need to find child. So we need to do std.mem.index of pointer to node. Haystack is ptrs. Needle is, we need to index of scalar. Is child. And that gives us the index. Const idx equals, and we assert that it's present because if it has to be present, otherwise we wouldn't be here. So then we do ptrs at idx equals ptrs at, you know what, we can even save this. It's maybe not a bad idea. If the last is different than child, then ptr is last. What music is in the background? It's a piano, relaxing piano radio on YouTube. Okay, so we swap them around, and then we also need to do the same with the bytes. So we do node.bytes at dot slice at is this slice, and then we do bytes at idx equals bytes at bytes.len minus 1. So we move the last value to this index. And then we shrink. And then we do resize. So we do... Oh, also remove child, returns a new pointer. So node return text dot resize. So it's node, it's GPA, it's n, void length is n dot bytes. Well, I guess it depends on, you know what, well, let's put 2 calls maybe. We put 2 calls, or do we switch again? Maybe we can put an if. Okay, what is the resize going to be? Value is going to be n dot value. Bytes is going to be n dot bytes len minus 1. Huh. Pointers. What is it going to be? Max between 1 and n dot bytes of len minus 1. Oh, that's actually not even it. I think that this resize needs to be copied so that we don't go insane. 1 here, 1 here. Okay. So in split, void len is n dot bytes dot len, and we are gonna want pointers to be n dot bytes dot len is 1. Same as this. Up here, we want to... Oh, you know what? I think that what I'm doing with merge is wrong. I think that the merge case is different. So I guess we will want to shorten it. Basically, I think the pointer stays 1. This is our coded 1. This is 1. And I think that bytes... But it's probably not even -1, is it? Oh, you know what? I actually don't know what's going on with merge. We'll probably need to do something different. Okay. Let's take a look at the C code. Rax remove child. If the parent, okay, so this is the merge case that they didn't know what to do about. So what do they do here? If the parent is a compressed node, they set everything to 0. Oh, a merge node turns into a split node with nothing in it, right? Because merge nodes, like zero length merge nodes, basically. So we zero it. We straight up zero it. Okay. So okay. So we resize this. So this has pointers 1. Pointers goes to 0. Bytes goes to 0. And value stays the same, I guess. And this is actually it. We simply resize everything to 0. Well, no, almost. Layout needs to become split. There we go. Everything else will be taken care of automatically. Then let's take a look at the split case. Let's see, order wise. So if it's not a merge node, or you know what, we can save this. Otherwise, we need to scan for the child pointer and mem move accordingly. To start, we seek the first element in both the children pointers and edge bytes into the node. Rax node, first child pointer. Is this going to make it super complicated for no reason, man? I think this is the same thing that we're doing, just super complicated. Let's double check. To start, we seek the first element in both children pointers and edge bytes in the node. Okay. Then we search the child pointer. To remove inside the array of children pointers. Remove the edge and the pointer by mem moving the remaining children pointer and edge bytes one position before. Yeah. In our casing, we're not doing this. We're instead swapping the value with the last. And then we're expecting the rest of the code to do the rest of the work for us. It's slightly different, but it doesn't really make a big difference, I believe. So yeah, I'm not doing it like this, but that makes sense. You know what? We're not going to copy this since we're deviating. Also, we need to make sure that resize does what we expect. Will resize deal well with copying stuff when it shrinks? No, it won't. Look at this. Oh no. You know what we're doing here? So look at what we're doing. We're copying. For each delta, we're looking at At the new offset, we're copying all the data with the old size, copying it from the old size to the old size. Problem is, we need to do this needs to be the minimum. This needs to be the minimum between old size and new size, because there's also new size. Wait, you're not using what? We're not using new size? Bro, where's the new size? Old size, new size. Where's the new size, man? Um okay, where were you doing old size? Field size. Okay, what is this? Let's see. Field length is this. Yes. Yes. Okay, this is more than old size. This is like literally size. And it needs to be the minimum. It needs to be the minimum. So we don't call this old size. We just call it size. And then size is the mean between the field size and the new size. I guess we cannot compute this here. We need to compute it here or here, I guess. Okay, let's see if we can make this work. So we're resizing. We compute the original size. And then we say, okay, was there specified a new size for this? If there was no new size specified for it, then this can stay what it is. It stays what it is, so we're just gonna need to copy it over. Sorry, and then this is correct. But then in this case, then we need to copy over the minimum between the field size and there we go. It has to be this. Yep. Because if the new field size is 0, for example, then you don't copy anything. You shouldn't be copying anything. Okay, and then what if it's void? Void has, I think, the same problem. Void also needs to do this inside here. So there's a void field, but we don't mention it. So we have the void size. Wait, why am I repeating this calculation? Look at this. So it's going to be void size. But in here, new field len, There we go. There we go. Okay, this should be good. Okay, so we have this. Actually, I wish I knew if I have regressed any test right now, but we have too much stuff that we need to go through first. Okay, we call Rax remove child. And then if new is different than age. Actually, this is different, right? Because this actually does not return any pointer node. It returns a optional node. Because resize returns null if it doesn't return anything. So we can do this. If new, then we do stuff. So this is the case where parent is null. If parent is null, then parent link is set to Rax head. So that's ampersand r dot root. Otherwise, if there is a parent, Rax find parent link. Also need to implement that. Parent link is Rax find parent link. In a parent, which is a pointer to a node, and another node, which is the current on H. So find parent. What is find parent link? Find parent link means that we are searching in the parent node where it is that we link to H. Because we need to replace that. We basically, I haven't read the next line, but I'm guessing the next line is going to be parent link dot star equals new. I'm guessing, right? Right? Oh, regardless, right? It's kind of we do it regardless, but it's here. Here's we write new to parent link. Also, no, it's slightly. I got it slightly wrong. Did I? I might have gone. I might have gotten something slightly wrong, but not terribly. And also, we can do this. There we go. We can remove curlies. Remove these. There we go. If parent, then we grab P and we return this guy. Otherwise, what if we were everything on a single line? Yeah, no, way too much stuff. So Rax find parent link. It's gonna be parent dot find parent link of A to H. Oh, and this is gonna be P. Well, actually, now this is much shorter. It's still not gonna fit, I think, but oh yeah. I've been binging Cristo S. Really? Well, glad you're enjoying it. Doom. I'm working on a Radix 3 right now. But the US stuff was cool. Yeah. I mean, the book did most of the heavy lifting. And Jacob Lee in chat also helped a lot. But yeah. And so let me see if what we're doing makes sense. We're saying the parent link is also parent link is defined in here. We're not defining it outside. So it's really short-lived. And it's basically, yeah, it's basically us just being able to find where node P points to H, returning a pointer to that location so that we can write to it. And I think I got this right. So let's go implement find parent link. So this returns a pointer to a pointer to node. So we do return node. It's gonna be std mem dot index of index of diff compares two slices and returns the index of the first inequality, returns null if the two slices are equal. Span slice 2 len index of sentinel all equal, trim start trim and trim index of scalar last index of scalar pause index of any last index of any index of none index of yeah, okay, so we don't have we only have index of. I mean, we could do it easily, right? So for n dot ptrs dot slice, and then we accept those things by pointer. Which we can do. Slot. If slot does star is child, return slot. Then we said it's unreachable. So we have implemented it. We really don't even need index of. Up here, index of is convenient because we're reusing the index elsewhere. But here we can just straight up do this. This is the most straightforward way. Okay. If after the removal of the node, if after the removal the node has just a single child and it is not a key, then we need to try and compress it. Okay, so after this if, oh, but this is still basically looking at new. Give me a second because this is still looking at new. Well, we need to be looking at new all the time. No. How do we deal with this inconsistency between us and them? Also because h equals new. I guess we can do h equals new here. Yeah, we can do it here. H equals new. And then down here we do if h dot bytes dot len is 1. So it's basically this. Also, we're using child, we should be using ch. Okay, so here we have try compress, which is false. Obviously, it needs to be var because we need to mutate it. Then we mutate it here. We say try compress is bytes equals 1 and the value len blah blah blah. This is the end of the if. This is the end of if child also. Okay. Actually, wait, what am I doing? It's this. This ends here. This ends here. So we're at the end of each child, and we are looking at. Oh, and then we are then also going to the next one, and we're adding an else. So if size equals 1. Okay. So if I compress was 1, then if try compress was 1, then we just want to toggle it off. Can we do this? Try compress and equals stack dot ohm. Is it allowed? Am I doing a bad? It's and not, right? So if this was true and this is false, then it's true. If this is true and this is true, this is false, correct? If this is false and this is false, we stay false. If this is false and this is true, we stay false. Okay, so we have the compression algorithm. You know what's interesting is that this is not needed. We can do it, but basically we can also just return value. We can stop here because for now, I mean, because since it's optional, it would still work. It would be suboptimal, but it would still work. Local variable is never mutated. Yes, indeed. We never even used I, did we? But there is also a bunch of stuff we haven't implemented where probably I becomes more interesting. Maybe. 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 So here we have I. Can I go to references on this guy? Yeah. Okay. Let me go to references on this guy. Oh, it's literally just used right after. So never mind. This is a const after all. Did we break anything? We did break some stuff, didn't we? Extracted one arguments, found 0, 180. Right. List of what? Pointers to node. We haven't broken anything. This is good. At least we haven't broken anything so far. So we should be able also to delete stuff then and not see anything break, right? So here's the idea. We add a Nibalesco and then we remove it. So we do we fetch remove one that isn't there. Let's do one that maybe tries to find something. So we can even do try std.testing.expect null. Is there expect null? Well, we can do this. Now the problem is that if we do it, let's try. Let's see what happens. Expected two arguments found one. Okay, let's go. More stuff that we need to fix for 472. Okay, what are we missing from the stack? Oh, right. No field memory function named get 482. Yeah, get PTR. Dot star. Cannot the reference not pointer type optional use size. Right. So this is an optional T. And we have to do this. There you go. The fuck did I do? Except a reunion type found use size. Oh, right. Remove can't fail. No, you don't try it. No, the init in optional racks 500. Yeah, this whole fucking child thing I don't get. This whole thing is sus. I have no idea what the heck we were doing in there. Remember Franklin expected two arguments. Oh yeah, what do we do? Dot single. Expected type array list found constant array list. Yeah, I imagined. What is that? 192. I guess we need a mutable stack. Type info, blah blah blah. Okay, 149. We're missing a try. Oh, now it's optional. Right. Now it's optional. Man. Or else. And the layout equals dot split. Turn n. To be honest, this decision to return null, I'm not loving it, but so for now. But type root racks no does not support field access. 157, 157. Oh yeah. Because this is n dot bytes dot len, of course. Although we can do it like this. There you go. Yeah, because we need this in any case. Expected root rax node found optional root rax node. 524. That's n. Next. Unbound for loop. Whoops. Find parent link. What do we know about node when we call it find parent link? Do we know what the layout is if we're calling it? Child ch parent. No, because we just popped it. We know nothing about this node. Okay, so far so good. So after fixing all the programming errors, so far so good. Now let's remove Annibalesco and see what happens. So now we remove something that actually is there. I'm gonna leave this test. So this test should fail now because this should not be null. This should return something. Yeah, expected null found 1,000. Indeed, that is correct. So 1,000 it is. And now expect this to fail because it should say that it has not found it. Unexpected result. Yes. Perfect. So we say expect not existing. Correct. This is working. This is working indeed. So we're missing the like recompression implementation. We need to wire in this into the unhappy path of insert. And that could uncover bugs, of course. But it seems that we're doing good. So I would say that the meat of what we needed to implement has been implemented. There are curious design questions about whether what we should do with allocation size and what we should do with allocation resize, like when shrinking. To be fair, the fact that removing something for the tree could out of memory and leave it in a broken state, it's not a great property. It makes for a much more fragile data structure that really can't take a beating anymore, like at all. So that sucks. Um, mm, I need more tea. But maybe we can. I think we're at a point where maybe we can try to benchmark this guy and like race it against this implementation and see how it goes. And see how it goes. We can get maybe a dictionary of, I don't know, like 1,000 words or something, and we try to make a tree that where we add these 1,000 words. Time to poop. Time to poop. It's pooping time. Oh man. Hey, Neurosite. Okay. So let me think. What do we want to do? Well, I need to write this to wire this where it needs to be, right? Here we go. Resize for data, catch panic to do. Um it's a panic to do somewhere in here. You know what? We need to read the C implementation. What's it called? Rax insert. Rax generic insert, right? So this language is not too grabbable, huh? Blah 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 blah. Rax set data. Get data set data. Blah 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 blah. There we go. Here we start getting more into the meat of things. There we go. If any of these bad boys end up being null, we free all the other ones and then we return. So far, so good. The problem is when we run out of memory later on. Where do we run out of memory? I don't think it's, is it here? Here we, no, this is another case where we're good. It's after this. It's in the while loop. Yeah, we can run out of memory. I think this is it. Yeah, Rax compress can and that makes us go to So it's the two branches of the while loop. They make us go and this is the So let's see how that looks like in our case. So in get or put, we are the while loop, and the two ifs. Yeah, look at them. Catch, panic, to do. So what does the look like in here? It takes in H. So it looks at the current node. Sets is null 1. Sets is key 1. Let's see. This code path handles out of memory after part of the subtree was already modified. Set the node as a key and then remove it. However, we do that only if the node is a terminal node. Otherwise, if the after relocating a node in the middle, we don't need to free anything. And we do that by saying that size is 0, size of h. So if if h is an empty node, then we want to remove it. But we make it a key, and I'm guessing making it a key has an impact on Rax remove. Ooh, also Rax remove takes in a bunch of parameters. It takes in the Radix tree, fine. The string, the input string, plus the offset that we got to. Oh shit, and it does not take h at all. So, okay, we're basically saying, yeah, okay, I get it. We're saying, look, let's imagine that the current node is actually a key. So we make it a real insertion for a brief moment, and then we remove it. And what is I in this whole mess? It's up to which point we have inserted. Yeah, so we need also I precisely because it's going to be a prefix of the entire string. Because if we were able to fit the entire string in the Radix tree, we wouldn't be worrying about this stuff in the first place. Okay, so catch needs to call r.fetch remove GPA, and key is going to be key, in our case, key from 0 up to I. And this is also what we want to do here. But the problem is that we want H to be a key. The problem, though, in my case is that, well, the question is, will this node be a key for real? The answer is no. Oh, this is annoying. So since we cannot decouple this state from the concrete state of the allocation, we're in a pretty shitty situation. Let's also double check what Antiros was saying. So the code file handle out of memory after part of the sub3 was already modified. Set the current node as a key, then remove it. However, we only do that if the node is a terminal node. Otherwise, if the happened reallocating a node in the middle, we don't need to free anything. So what he's saying is only if this node has size 0, we call Rax remove. So we need that check. So that's basically how it is. But then we are also modifying the state in order for fetch remove to do something, because fetch remove will not do anything if the node where it lands is not a key. Well, if it doesn't have a value, basically. Let's see, fetch remove, return value is these elements. Try compress. Well, I mean, wait a second. We see that we merge fully. We try to grab the return value. And here I'm doing this because I'm not sure that this value will be like that this is a node that has a value. So try compress. If this is equal to 0, wait, are we even checking? I feel like there's something missing in here because there's something sus. If I is different than keylen, which is going to be false if we match completely, or the layout is merged, or we are in the middle. Oh, I think this is it. It's rack slow walk that does it, right? It's rack slow walk that looks if the node is key and uses that to decide if to set J to 0 or something like this. Do we even care that the node is key? Oh no, here we don't care at all that the node is key. I think I'm missing a piece of understanding. How do we know that we didn't land in just a random node that wasn't a key? Like here I'm testing for this stuff. And we do Rax get data of H. So, okay, so here, basically, it is guaranteed that if we get here, okay, so looking also at the structure. Oh. Oh. There's an explicit check. Do I have that check? Of course I don't. Whoops. There we go. Okay, so we currently have this problem, which we could solve if we did something like this. This is how we would solve it. We call fetch remove. Let's call it remove impl. Call fetch remove with false, which will make us remove also nodes that aren't keys. And we just do not expose this. And you know what? In remove input, then we can also do null. Oh, this is actually nice. Go to remove impl and we say, look, it actually returns boo. And we say keys only, and then takes in pointer to value PTR, which is a pointer to T, optional pointer to an optional T. There we go. Oh, actually, it doesn't need to be optional. It just can be a pointer of T. So we can do class return, well, var return. T is undefined. Pass down a pointer to a result. And then we say if success, return blah, 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 otherwise return the other one. And so here we say if so return now, we return false. And here we do if beta star equals issue value dot get ptr. And we can assert this because we know that it's not going to be conditional. We assert and it's going to be here. We can also do this assert is only is the same as value ptr equal to null. So if value pointer is null, then keys only needs to be present. If value pointer is different than null, then keys only cannot be true. No, I'm not sure I'm doing it right. Give me a second. Give me a hard time overcoming how item paths work in Zig. Come from Rust. Any tip? I don't know what's an item path. What's an item path? What is item path? It's like foo.bar, like accessing fields. So let's see. Let's see here. So if value pointer is null, so if this is true, then keys only has to be true. And that is wrong. So I think I'm overcomplicating this freaking thing. You know what? Let's write it down in a dumber way. Keys only is false and value ptr is different than null. There you go. If keys only is false, then value pointer must be different than null. No, must be null. For example, here we'd say true. Yeah. There we go. This is what I wanted to say. How to navigate modules, namespaces to find items like function structs, enum, more types. The answer to all these things is dot. So you import std, and then you access definitions in it with dot. And dot is all you use all the time, every single time, no matter what you're doing. If you have the LSP set up, then you can go to definition, and you will find that the file, and you will see that you're basically importing std.zig when you import the standard library. And this file is going to be in your file system, and you can also find it on GitHub, and it's like readable. So it has all the re-exports. And so here you can see all the namespaces that are available to you. And you can see all the types. There's a convention in Zig where lowercase name means that it's a namespace, uppercase name, uppercase, Pascal case name means that it's a struct that you can create instances of. In Zig, there is no distinction between a struct and a namespace. We use structs to define namespaces. So, for example, let's take a look at built-in. Built-in, you're not seeing it here. You're not seeing very well here, unfortunately. But the point is that namespaces are not their own concept. So you're just basically, all of these are struct definitions, and each one of them is in a different file. And yeah, you just navigate them with a dot. That's it. That's all there is to it. Right. This was implemented in Cine as a go-to. So what do they do after the go-to? So on the they do this. They do say that they got an out of memory condition and they return 0. In our case, well, we do this and then we return error dot out of memory. This is what we do. This is so much better than the C version. I'm so sorry, man, but this is so much better. Let's see. Found void 442. Oh yeah, no, we return out of memory no matter what, not only in the if. We do that unconditionally. Expected that usize sound pointer to usize. Yeah, 512. Oh, we got a failure. Right, because this assert is half the story. Man, that assert, I'm so either is only or this stuff. Which I guess can be simplified. Now we don't complain anymore. Okay, let's see. Okay, but is there a way you tell if the item is just a struct or enum or function or dot 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 right away? Well, for example, here 3 is a definition that I made. I go to definition. This is a generic type, so it's kind of weird, but let's look at this one that is non-generic. You see that you assign a struct to it. And so we'd go to definition, for example, allocator. What the heck is allocator? Is this going to be a struct, an enum, or something else? Go to definition, and it brings me into a file that is, I know it's a struct definition. Let's see something that isn't a struct maybe. Functions you can recognize because they don't do a Pascal case. They do camel case. So they have a lower case letter initially, or like, I don't know what you want to call it, JavaScript case. So lower letter initially and then upper letters. That said, it's not a hard rule. So it's just a convention. But like you can go to definition and you see that functions definitions have this signature. Otherwise, you need the LSP to help you with that. I'm sorry, but I'm not sure how to interpret this question. So, like, usually on simple names you go to definition. And so if something is a struct, here it will tell you that it's a struct. It's something is something else. So, like a function definition, you see because it's pub fn function name. Enums will have, const foo equals enum, blah, blah, blah. Also, be aware that if you come from Rust, be aware that what you call enums are not enums in Zig. You think of enum as something that can also have payloads, but enums in any language except Rust cannot have payloads. What you call enum with payloads, we call tagged union. So you will want to see a tagged union. And if you want to know what the symbols are for these things and how to like make one, what's the related syntax, go to ziglang.org, you click documentation, and then you scroll the language reference and you learn about it. So for example, let's take a look at unions. Union. So this is a union where you have cases and payloads. It can be whatever you want, but also be aware, this is not a tagged union. This is just a union. A union doesn't have a tag. It doesn't store runtime information to know which is the active case. The assumption is that you're using a union. You will be able to know what the active case is in some other way. Something else will be able to tell you what is the active case. So then you can have a tagged union. So here you can see we define an enum, no payloads, just tags. And then you can create a union off of an enum. And they have to have matching cases. This is a very explicit syntax. Usually you don't do this. Usually you just do this. You just create the union and then you say that it's not off of a concrete enum, but you just put the enum keyword in here and then you basically create everything in line. And so this is a union that knows what is the active case at runtime. Also, if you want help with Zig syntax when it comes to the basics, go to Learn on the Zig website, scroll down, and take a look at Ziglings. It's listed under online learning resources. You look at Ziglings, which is a collection. You actually have these in Rust. Like Ziglings has been, let's see. It has been inspired by Rustlings. They actually do say this, I think. I don't know where they say this, but they used to say this. Here we go. Inspired by the Rustlings project. So if you've done Rustlings, it's the same thing. If you've never done Rustlings, Ziglings is basically a collection of tiny Zig programs. They all have mistakes in them. Yeah, make sure I'm not a bot. So they all have mistakes in them. And then there's a comment that tells you how to make it right. And so if you follow the README instructions, they will tell you what your workflow should be, which basically amounts to running Zig build, immediately getting a build error, and then you fix the program, and then the first program will build correctly, and then you can go to the next one, etc., etc., etc. I think we're good with the basics now. And since we're good with the basics, I think it's time for benchmarking. To be fair, we don't know yet if this implementation is fully correct. It's nowhere near as test as the other one. Unfortunately, to really know this for real, we could run maybe the test suite in the other implementation, but even better would be fuzzing. What we would want is to be able to run fuzzing. The problem is that AFL++ is broken as fuck. And we need Zig native fuzzing, which we don't have yet. So it's coming, but it's not ready yet. So especially not ready on macOS. I mean, it's not really ready on any platform, but macOS is especially broken. So none of that for now. Okay, let's remove my random prints. I should probably comment this stuff out as well. Okay. So how do we benchmark this stuff? Well, how do we build also the original one? I think we can just build everything here. We can make a test, like a target for it. Or rather, maybe we pass in a flag. How do we do this? Technically, what we would want is another project. It's a project that imports both Zig racks and the other racks and uses them both. But at the same time, it's just a main function with some silly stuff in it. So it should be trivial. Let's do the Zig one first. So, oh, but we do have a dependency. So never mind. We do have a dependency. Okay, let's make bench.zig, I guess. Benchmark.zig. Up and import std. Why am I doing this out of order? Const racks and import racks. To have function main void, and in it we do like 1,000 inserts and then 1,000 yeah, the heck do we do then? Just do 1,000 inserts. Var r equals racks dot init. Also, we don't have racks or anything because we don't exist in the build system, so let's fix that. Const bench equals b dot add executable. Root module equals b dot create module dot root file equals root source file is b dot path source slash benchmark zig. Last question: does the dot curly works to init structs only with default values? No. So if you leave it empty, the assumption is that every field in that struct has default values and you're using all the default values. If the struct doesn't have all default values, so if your struct looks like this, const foo equals struct, banana, usize. If your struct looks like this, then you cannot do f equals, like const f equals colon foo, and that's it. You cannot do just this because it's missing banana in it. I think I can even show you this. If instead of putting code in a random place, I put it in here, I think you will see the problem. Let's see. Okay, let me see if I can fix all the different problems with the code that I was looking at. Missing name, yeah. Here you go. Okay, there we go. So look, it says struct field missing banana. But if I do give it something, a default value, then it's not a problem anymore. So if I take this out, then what you have to do is this. And now it works. Trailing comma or not, it doesn't change anything. The trailing comma is used by the formatter to decide vertical or horizontal layout. That's it. But you have to specify the field. And if banana has and if foo has something else, like I don't know, this bool equals false, then you don't have to specify it. So they should give you an idea of how this feature is supposed to work. No, what the heck am I doing? Here you go. We want this shortcut. And then it's missing a module. Dot imports equals no field imports. Because it goes inside here. Now we should be happier. Why are we not happy? Why are we not happy? We should be happier. What's making you sad? The root module of a compiled step must be created with a known target field. Oh, there we go. So this is the problem. Yeah. Let's see. Unused local variable. Okay, so we're back. We're now happy. What is the problem now? Yeah, unused local variable. We also have some other problems. Can we go to definition? Will it work? Yeah, go to definition works. So that is not the end of the world, bro. There's no init. Oh, right. Rax has rocks. So do rocks of what? So the C version adds pointers. I guess to make it comparable, we should also add pointers to it, or like usize is fine. Like the same data type. Because if we for example, if we make our version void, then things go out of whack compared to the original version. So now we can do this const r, well, var r. And now there's a question about the allocator. So if you raise the Zig version versus the C version, if you raise it that way, the problem is that well, there's going to be a difference in the allocators. So we have to, I guess we should try kind of both things, right? We need to try the C version, the Zig version, and see what happens. And we need a dictionary. And we need a dictionary. We need a dictionary. Also, Rax, what does it have in it? It has the C, the H. I think everything else is not really strictly needed. CRC16, malloc, test. I think, well, for example, Rax.h doesn't need any of that, right? stdint seems to be the only import in here. What about the C1? stdlib string assert stdio or no math Rax.h. Yeah, that's it. And then if you're doing if not defined raxmalloc include, then you also want raxmalloc.h. So that's also the last header file that we need. Although it's super dumb and minimal, so that's fine. Okay, so it should be easy also to get Rax to build. Where to get a dictionary of like, I don't know, 1,000 words? List of words. You know, like 1,000 words or 10,000 words, whatever. 1,000 most common words in English. Wikipedia, list of 1,000 basic words. Where can I download this stuff? There is some. The Linux one? I don't know. Is there a Linux one? Text file containing 1,000 words or something. I don't know. English words. Containing 479,000 English words with all your dictionary word-based projects. Auto-completion, auto-suggestion. You know what? Fuck it. Let's use this one. I was saying 1,000. How about 475,000? I'm up for it. Is this the bad boy? Or just the zip versions of these guys? Let's see, it took me about a year to properly understand how async Tokyo in Rust really works. Hoping Zig team will have learned enough from other languages to land far better alternative for asynchrony. Did you see what we published recently about the async stuff in Zig? Also, I would say that the Zig team has learned mostly by not looking at what other languages do. Because you know what's, I mean, okay, so the fact that you say that you hope it lands soon, it means that you are aware of what's happening. But I'm referring specifically to this. For you or anybody in chat who has not seen it. User share dict words. Okay, let's see how the Mac fares on this. Yo. 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 Thank you, Der Teufel. Also, thank you, Apple, for not sucking for once. Well, check this out. So I cannot just at embed file that file because is hey Andrew, 3 is ready enough to be used. Yeah. So I cannot just add embed file the file from my disk. Although you know what, maybe we could by copying it you know what? Copying it is probably not a bad idea anyway. So for benchmarking purposes, so copy user share dict words, and we move it to, well, we copy it to source/words.txt. Although, you know what? That doesn't, I don't like this. It shouldn't be that. It should be something like bench. Because the problem is that if we put it under source, then let's put it under source for now. We can think about it later. Fuck it. Okay, so we can do it. So now we can do this. Embed file words. Maybe we should give it a txt. Oh, I already did it. I'm smart. Okay, so I can go to definition. No definition found? Dude, are you joking? Oh, I think it's DLS that is just not being smart about it. Okay, so we have all the words, and then IT is, well, var IT. It's a big file. Why embed it? So that you reduce the amount of machinery that you're involving in a benchmark. Why not embed it? Let's see. How big is it? It's like 2 megabytes. Whatever. It's fine. SDMM tokenize scalar type u8. Buffer is going to be words. Limiter is going to be a new line. While it.next. It's going to be a word. What do we do with the word? We add it. We try r.append. Oh, we haven't implemented append. We have get or put. We goop. Also, we need a reference to GPA, so never mind. Const GPA equals this. We need to try init. Man, good thing that result information permeates the try. Otherwise, we would be fucked. Okay, get or put GPA, and the key is gonna be word. And what do we do there? I guess the benchmark could be add all words, check that all words are inside. So we, stress this stuff. Although it's kind of silly because with get or put, we can actually do both at once. So, but in any case, it's fine. So we can do what? We can do this. If not gop.found, if gop.found existing panic. And then we say gop.value.ptr equals, I don't know, 42. And then we do, is there a reset? Oh, look at this bad boy. There's a reset. Basically, we do it again. We do get or put, but the second time we expect it to be present. And then we just say if value pointer is different, 42 add panic, bad value. By the way, this might very well just expose a bug in my implementation. So it might turn out that this is not benchmarking. This is actually still just testing. And this is it. Like this is the entirety of it. So this would be benchmark for Zig. And then we can basically re-implement the same, but we import Rax instead, and we use that one. Let's see how this works, how this goes. So can we zig build? Expected void found. Blah blah blah. All right, because main I took away this thing, but I shouldn't. So what's the problem? Cannot assign to constant. You're right, because it's value pointer dot star that we assigned. And also here it's value pointer dot star that we check. Okay, we built. It runs, and it doesn't poop itself. We passed all tests. Not bad. It means that the implementation is not completely wacky. That's good. It took a moment though, huh? Feels like one reason not to use a embed file is not to give the optimizer any clues about the data. Maybe it's able to fault stuff. I don't think it's gonna be possible in this case. Also because every time that we make a side effect, we're asserting and panicking, and I think that pretty much guarantees that LVM, dude, LVM wasn't even able to solve turbo basic stuff. There's no way it understands what to do here. But you know what? We can still change it if we decide to. So I think it's fine. Also, you know, it took a moment for it to do the thing, so it's not instant. It's actually doing work. Okay, so we have this. I think I guess I'm gonna move this to like something like benchmark zig bench. No, this is gonna be benchmark, and then we make benchmark C. So it's gonna be similar, but new right source slash benchmark underscore C dot zig. We write the same stuff, except we don't get Rax. We don't do this. And instead with C import const C equals at C import. Wait, can we use the new C import stuff? Has anybody used the new C import stuff on unstable zig? I don't know what the state of that is. I guess we can just C import for now and call it a day. I mean, if it works, whatever. Const C equals at C import. What is the new C import? Everybody's going insane. Well, I think that C import is going to be removed and replaced with a build system feature. So instead of being a language feature, is a feature provided by the build system. So yeah, so C import, and then you do C include rax.h, I believe. And I think this is the only thing that we want to do. And then we need gonna be able to do everything else. But let's wire everything with the build system first so that we can actually make it happen correctly. So I'm going to copy the bench code because it's going to be in some ways similar. So this is going to be benchmark C based on benchmark underscore C. There's not going to be this import. Let's see what else we can specify in here. There's like link libc, which is going to need to be true. Do we pass in C files? Can you pass C files, or do you need to do that afterwards? Yeah, you do it afterwards, don't you? Link libc is true, and then we do bench.add the file. I think it's just add C files. Is libc really needed for Rax? Well, yeah, because of global malloc, and also because it uses a bunch of other stuff from the standard library. It imports CDIO, math, assert. There's a bunch of imports of that kind. We wouldn't have to, I think, if we provided our own allocator implementation, but whatever. So what am I missing? Where's my add C files? Add C file also doesn't work. Do you do that on a module? Oh, you do that on a module, don't you? Add C files. Wait, am I going insane? Link this, link that. Add C source files. Right. Add C source files. I think in my case, only one is fine. Because we add rax.c, and that's pretty much it. So add C source file. How does this one look like? Lazy path, flags, language. Why is it just file and not source file again? Now this is going to be b.path. I guess we are going to need to copy a Rax also somewhere, which we can do. Yeah, you know what we can do? Check this out. mkdir benchmark move source slash benchmark.zig to benchmark. Same with underscore C. Move also words to benchmark where it belongs. Move copy rax slash rax.c. We want rax.c, rax.h, rax malloc. Come on, man. Rax underscore malloc.h. Why the space? I didn't put the space there, by the way. It did it by itself. I don't know what's wrong with this thing. C, h, malloc.h, and we copy them in benchmark. Actually, maybe we should make a Rax directory. There we go. Benchmark C, benchmark zig, Rax, words. Okay, let's go into our build system, and now we're going to need to make all this stuff work better. So benchmark is not from there, but it's benchmark slash benchmark. Benchmark c.zig. We give to it benchmark slash rax slash rax.c. No flags. Okay, nothing else. This is just it. Okay, so we add this file and then we do bench. Do we have to do it to root module? Can we do it to... Does this work? It works. Okay. And then we do bench dot add include path b.path mark slash rax. I think this is it. Then we look at benchmark C. We can't do this. We can't do this. So how does this work? Well, we have to use Rax basically. Can we go to definition now? Oh yeah, now we can go to definition. So now autocomplete is gonna work. So we can say const r equals c dot rax init unknown type name size t. Dude, I don't know. What do you mean? I don't know what size t, man. This is just wants std int. Give it, I don't know. It's std. This is std int bullshit. Oh, you know what? I think I know what the problem might be. In our build script, we say that this root module needs link libc, but it's more like bench dot underscore c that needs link libc. This is what needs it more than that module. Although, you know what? I might be actually completely wrong with this. I don't know if this makes any difference. But let's leave it at that and let's see what happens. Oh, you can't do link libc on root module, but you can put it here. File hash file not found. Okay, we're having some trouble here. Let's try to get the main stuff working, I guess, before we try to do more stuff. It expects you not to pass header files as opposed to source files. What? It expects you to not pass header files as opposed to source files. Not sure what you're talking about. So it's gonna be something like this. What's the actual correct terminology here? Rax.h. Oh, there we go. Rax new. Rax new and then Rax insert. Something like this. I think it's gonna be something like this, basically. Something like this. Okay. So let's see what's the problem with this. File hash file not found. Like this, maybe? But that should not be the case. It should just be this. Rax.h. Add include path. Deprecated. Use compile root module, add include path, lazy path instead. Oh, there. God damn it. Okay. So, so we were right in doing this. What are we missing? Maybe it's this that's failing. Benchmark / racks. The benchmark path is wrong. Oh shit, you're right. This is what's failing. Oh my god, thank you. Okay, and we're finally getting juicier errors. So unknown type name size T. But why is this the case? Why is this the case? Because I guess this is a C moment. So the problem is that Rax.h uses size T, and I bet you is size T defined in stdint or not? Is this stdint.h or or should it just be stdint? No, I think it's .h, right, in C. stdlib.h? Wait, no. Size T is not defined in stdint. Curse C bullshit. There we go. Now it works. Okay, what's the problem? Expected arguments found 4 in insert. Okay. Go to definition. I guess we can just open here. So what does it want? Rax. Right, we're missing Rax. So it wants R, then the string, the length of the string, and then a out data pointer, which it's optional because we're trying to insert something else. And then the old value. Now, I guess in this case, we don't want to do this. We want to basically get. So we don't want to call try insert, I guess. We want to call find. Want to call Rax find. We did not implement though Rax find in our case. Can I go to implementation? Of course not. Rax find calls Rax slow walk and then returns this. It's basically the same thing. Even though this is a separate function, I think our get or I think it's comparable to call this to bench this against our get or put. So Rax find, and that's it. And then const out equals this, and we assert that out is 42. Except for arguments found 4. Bro, what? What do you want from me? Data and then old. Ah. Old. No. Null, I guess. Expected type CU8 found const U8. Pointer cast. Also, what? It wants well, let's see what happens with the pointer cast. Are you gonna be happy with this pointer cast? Do you need more? No, you also need the const cast, huh? Please, no more. Expected pointer to any opaque found com time int. Yeah. And then again below. Okay. So benchmark runs. Benchmark C also runs. Yo, benchmark C is a little bit faster than ours. Uh-oh. But this is the bug. Also, maybe we should do a build of this stuff with the SMP allocator one with something else. But for now, let's see. So let's benchmark and debug builds. So hyperfine. Wait, let's do poop. Poop zig out / bin / benchmark zig out bin benchmark C. Right. So C wins a bunch. Let's look at memory usage though. Peak RSS 15 megabytes, peak RSS 90 megabytes. Yeah, we're a little bit bigger. Oh, you also know why this benchmark is not going to be perfect, unfortunately. God damn it. So here's another problem. I'm not able to make my, where is it? I'm not able to make my struct packed. I would like for this one. I would like for this struct to be packed, and I can't because all the field parent pointer math goes out of whack with that because of a bug in Zig. And this is unfortunate. But I guess at least we can see what happens even without it. So we're never gonna be on par when it comes to memory, but at least we should get close. So let's do Zig build dash release fast. So we're making 2 release fast builds. Let's see what happens now. Can you do extract with lines to pack it more? Maybe. I don't know if that breaks field parent pointer or not. So in any case, so look, we are pretty much comparable in release mode, and I'm not packed. That struct is not packed, and we are more or less there. The C version seems slightly faster. We use slightly more memory, as I was mentioning, because we can't pack. So what would the extract situation be? So extern, and then we might still fuck it up though. Let me think about it for a moment. No, okay, let's see what happens. With alignment, so we say something like this value has. Well, the problem is the boolean is still not small, right? It's still a byte in extern structs. It's not a single bit. That's the problem. I guess we can do it like this. Instead of 30, we do 23. Something like this. Let's see what happens. With build. No, something fails. What's happening? Extern structs cannot contain fields of type root lax node layout. Inode type U1 is not extern compatible. Only integers with 0, 8, 16, 32, 64, and 128 bits are extern compatible. Womp womp. So we can't do any of this. Problem is, if I select packed, then our math goes out of whack. Ooh, expected type pointer 2 found a line something something. Oh, this is interesting. Did I leave some online stuff in there myself? No. I just want packed. Like that is the right solution. The problem is that the math breaks there's a bug in the compiler, and also this is and literally it's just a bug in the compiler. If that gets fixed, I should be fine. What is wrong with h bytes slice? Expected type pointer to a array of u8s blah blah. Found weird alignment. Why didn't we have this problem in the beginning? Pointer host size 4 cannot cast into pointer host size 0. Pointer bit offset 2 cannot cast into pointer bit offset 0. Machine lag. You have a 1-bit field at the start. I do, and then I have another one, and then I have 30-bit one. So this should be 32 bits. So this should not be a problem. This should have a correct alignment, I believe. Although, you know what? Maybe when creating these type, I'm not giving it the overall correct alignment, or maybe I should specify it somewhere. That it does need a specific alignment. How do you do that? Can you put it here? No. Do you put it after? No, you definitely don't put it at the very end. Pack here. On the first field. So we can say that this is a line 4. Something? No, you can't override alignment of start field. Yeah, no, this is not it. Okay, wait. My point is, this is 32 bits. So this field should be fine. Actually, especially because this field is, wait a second, more on top of everything else. This field is a void type, so who cares? Oh, and in fact, right, the problem is with bytes. Okay, wait. This starts to make more sense now. Now it's bytes that has issues. Right. And that makes sense because we're packing. We're packing bytes. But then why is this a problem? Expected type pointer to root array, blah, blah, blah. Found a line 424. Can you try U1 instead of bool? Yes, I can try. I mean, I will get compile errors though because it will change some other metaprogramming stuff. Yeah, it's gonna complain that now I'm placing a bool where I should give a U1. I don't think this is it. A bool has size 1 impact structs. I think this has to do with us trying to call bytes not on a value but through a pointer. So I think that I might be wrong, but out of curiosity, let's go to 580. What if I do this? Is this better? No, this is still a problem. Is this where I should put the star? Cannot the reference non-pointer type. Okay. Is it the signature that expects a pointer to this and instead it wants a special alignment of this? But at the same time, yeah, I guess this would be a line and then of what? Add type info of P. I guess this can be std.meta.field. field info of P, and the field name is going to be ops.name dot alignment. Is it alignment? Is it just align? Okay, what do I get from field info? I get a struct field. Does it have an alignment? Alignment. Okay. I somehow assumed that this would have been automatically the case, but to be fair, it's actually not necessarily the case. Well, would you look at that? Would you look at that? Maybe we can do something about it. Like we can make a variable for it, so that it's not horrible to repeat every single time. It's actually slice impulse, slice get pointer, and init. So there's not a ton of stuff. Let's see what else is there. File align. Error alignment must be greater or equal than 1. Okay. This is because of void fields. Okay, so this is not correct. We were expecting line 1. But this is not correct, is it? This is not correct. Because we're not getting the precise alignment in the packed struct. Why is this a problem now and it wasn't before? Why did we get so far before before we got into this problem? Interesting metaprogramming conundrum. I don't know what the answer is. Because we would like to be able to say, yeah, look, this is a pointer to the specific alignment that you think it is. And this is what the function will give you. Okay, so I guess this stuff just can't be done. And well, in any case, I guess the quote unquote good news is that in any case, pack doesn't work for other reasons. So this also I will have to figure out once it works. But in any case, so in the end, it turns out that our benchmark, what is it? Oh, come on. But are you sure? Mm. Error scoop set timer count. Why is it erroring out now? It wasn't erroring out before, now it's erroring out? What? Something happened on my computer. Let's use Hyperfine. Let's see what happens with Hyperfine. Okay, are these the release versions that we're looking at? Yeah. Yeah, so the C version seems to win by a bit. Unfortunate. We need pack extracts for this to work, I guess. And then we also need maybe some extra metaprogramming fanciness, which we don't have. Although, to be fair, oh, you know how we can solve this maybe? I actually genuinely do not know. Well, so here's what I think I'm gonna do. I think I'm gonna call it a day. This has been everything with regards to the Radix 3 for now. I'm gonna need to consult with somebody and see what they have to say about what I'm doing. And yeah. So here's what I'm gonna do the next time. I think this Radix 3 stuff is as is for now. We can push flex. This is certainly something that we can do. Its status. I have a bunch of changes to flex that I haven't pushed yet. So we can push those because it's so much better now. We can also explain how to use it in the README. So let's do this. Let's explain what flex does. Usage. Const flex equals add import flex. And then we just say const my type equals struct. Foo usize bar bool buzz is a flex.array of, I don't know, an array of booleans. And we have the options where dot parent my type dot field name equals dot buzz length type equals well, like this. You know what? What am I doing here? This here when I could be doing this like in an actual source file. Oh, okay, it's fine. So create my type, and then you pass in the options. Also, you need try. Also, you need GPA. Let's make it better. Maybe person. And person has. I don't know if person is the right thing though. Maybe there's something better. Hmm. Let's leave it abstract, I guess. Maybe let's also give it an explanation. Maybe we could put the name as a. Oh yeah, thank you. We could put the name as the tail of a person. Then maybe would explain it. So as a simple one. So let's do this. Person, and then we say like we give it age and name. Age is a U size, or like a U32. I don't know. And then we say that it has a full name. It's an array of bytes. I was thinking, wait, why is this not auto indenting? Like this. It has a full name. Okay, abstract. Imagine that you have a person struct that has an age and a name. This is how you would define it normally. Age, use size, name, constituent. Notice, though, how this memory layout implies that a person and a name are expected to be distinct allocations. Um, note how this memory layout implies that the person and the name are expected that a person and a name are expected to be distinct allocations, which you can connect through the person.name slice pointer. What's a good drawing? There are some like drawing thingies that can be used to create like ASCII graphs. ASCII graph. ASCII flow. Oh, well, that looks good. Okay, can we clear this? Um, oh man. Control something, Alt something. No, delete. Okay. No, bro, I swear I haven't clicked. Why am I forced to? I hate this thing. Delete. Okay. Now I don't have a force click. I don't have a force click. Sorry, force click. Now I can do this. I can do a line. Why did the line go there? How do I move this thing? Mouse clicking. Please give me something better. That thing is ass. Yeah, I'm trying to draw. Oh, this one doesn't seem horrible. Let's go. Let's go. Oh, actually, text. Okay. No, I do. How do I commit the text? Okay. So now we can I resize this? Bro, you make it look like I can. Okay, I can. Oh, arrows are in the middle. I see now the difference. Well, how do you delete this thing? Oh my god. ASCII Unicode. How do you delete it? I swear, why are these things always so broken? I'm trying. Oh, maybe backspace doesn't work. Space, new line doesn't work. Del. Um. mm, I don't even know if I have it bound. Actually, I don't think I have. Bro. Draw you, but I want one that turns into I want one that turns into a um yeah, into asking for markdown. look at this genius idea of being able to delete. But I'm actually surprised that this one up top works this hopefully, because usually this one should be fine, right? Select a move. Also, if my mouse goes up there as I'm clicking, it will it was moving my browser earlier. But select a move, it's fine. But how do I navigate this grid? How can I move around this grid? Why are these people like this? Yeah, you know what? I guess I'm sold. I'm just gonna do it here. Like fuck these people, but god damn it though. Jesus Christ. Yeah, I'm actually way better on my own. No, whoever suggested to do this right away was right. Also, on GitHub mermaid diagrams, never use them. I don't have any thought. I'm vaguely positive about it, but that's it. And you don't need to start importing in person if the bytes for name are immediately after the struct. And I guess we can show like an updated version of this. Well, more than this, Mm, guess it would have to be like this, maybe. Not exactly, but Lori Scroll. Yeah, I'll take it. I'm not being too precise about that, so I guess it doesn't matter. The problem is that we need the length, though. We should call it nameland. Problem is that it forces us to make a chunkier struct, but mm, I think this is fine. Would you use U32 or U64 for length? I don't know. Mm, this is a kind of a silly example. In a realistic scenario, you usually do this stuff with a packed struct. And so in a packed struct, you choose for length whatever bit size makes sense for your packed struct. It's just that we were kind of making a silly thing here. So grab bytes, and then we say GPA dot free bytes 0 dot dot p dot size of p person plus name line. Well, let's do it this way. The C programming language offers flexible array members The bin variable length, they don't really fit into slices themselves, correct? Lack of VO1 indexing leaves me hesitant. The composability is limited. The use cases are real. Yeah, you can't access in O1 every field, but the idea is that you don't have everything that you want to have non-variable, you keep non-variable in the struct, and it's just a normal struct. And then you usually have like a tail of data with one or two, or let's say three optional fields that can move around. But then at that point, the memory savings that you get from having one contiguous allocation are worth the extra math that you have to do to access things. Keep in mind also that once you have an index into a slice, you have it, and then you can use it. And at that point, it's a normal slice. And the math that you have to do is not bad. It's like a couple additions usually, so you're kind of good. If you look at anti-rex racks, that's one example where this type of stuff makes sense. There's probably a plethora more. Does anybody have any good example here? What is the network example that Andrew was providing? Although for that one, to be honest, what we're doing here is not really that important. I'm just gonna put anti-rex hierarchs here, but there's plenty more. Man, my own cuckoo filter array also would have benefited from this. I just didn't do it at the time because it was too much stuff. CMSG netlink. What's CMSG? No. Where did I land? It's fine. I'm gonna leave this for now. So Flex is a more typeset implementation of flexible array members from C. Flex will give you the ability to have more than one trailing, let's say more than one flexible array. I guess I'm just gonna leave it at that. Man, what was I doing here? What is it, 9? The DPI is disgusting. Okay, so you know what? For now, maybe we can leave it at that. There's obviously more work to do. Um, Maybe we can do name and surname. Again, I was thinking, wait, why is this not going on a new line? Hmm. So here's the thing: the resize API is right now is horrible. It is really horrible. So resize is a flexible struct. Um, if resizing return requires moving the data, the new pointer will be a pointer to the new location. Pointer to the location will be returned. Sizing will reserve will move data So what I want to say is that when you resize, the data also gets moved for you. Hmm. If resizing requires moving the whole strat, a pointer to the location will be returned. Same as realloc. Yeah, I think yes, but realloc, I think it's kind of different because I think you should think of this more of an array list than what an allocator does, because this is content aware. Like realloc will copy the whole allocation for sure, yes, but here there is more nuance to this. Resizing will also move data according to the new length provided. If for a given field, if the new length for a given field, new length greater than old length, um, all old data will be copied, new bytes will be undefined. All length greater than new length, only all data that fits will be copied. Uh, discarding all data from the end, e.g. 1, 2, 3. I don't know if this is a great explanation, but that's kind of what it is. Okay, I guess we can make some that explanation. But I really need to improve this API. This right now is really bad. Yeah. Okay. Well, I'm happy. This is cool. Do you think something like length type LEB128 would be worth supporting? I don't even know what's an LEB128. It would be for cases where payload length varies a lot, but it's usually so small that length overhead becomes meaningful. What's LEB128 then? Little Endian base 128 is variable length. Code compression used to store arbitrarily large integers in a small number of bytes. Oh, I see. Holy shit, we support it? Interesting. I need to learn more about this. Um, I don't know what the answer should be. Here's what I do know. Um, if we had working pack structs, so we don't have working pack structs, so um, that's kind of a problem that needs to be fixed for this to be meaningful, I think. But assuming that we do, then I really think that usually like that probably trumps every other need that you have. And in reality, what I'm seeing from Rax and my own interpretation of things is that usually what you do is just you try to get clever in other ways. Here's an example. You can use null delimiters. You have usually here's an idea. You have length that varies a lot. Null delimiters are one good way of doing it. Another one would be, for example, that let me think. Yeah, you're saying, let's say that you have length that really varies a lot. I don't know, maybe, but wait, how can LEB give you all integers in fewer bytes? Oh, because it's variable length, right? The point is that it's variable length. Do you want variable lengths? I don't know. Maybe. You know what? Maybe it would make sense. Maybe yeah, it would make sense. I think we could do it even okay, if Zig has it in the standard library, then that's great. We could probably do it without needing anything. Like I guess it's up to me to implement this stuff, right? When would you use it? Like for search. Like you're implementing a search thing and you want to be able to do fuzzy searching, for example, or you want to avoid paying the price of having in memory multiple copies of the same string when they have common prefixes. So yeah, you know what we can do also. So we've been testing. So we've benchmarked. We benchmarked R3 versus the C1, and the C1 wins. Here's what we can do. Let's test the Zig one with not the SMP allocator, but with the C allocator. So C allocator, and then we go into Rax, and well, not in Rax, in benchmark, and we do dot link libc equals true, dot single threaded equals true. I don't know if that makes any difference, but we couldn't do that with SMP, that's for sure. I don't know. Let's see what happens. So Zig build release fast. Yo, it's worse. SMP was better. Yeah, SMP was definitely better. Jesus. So no link libc. Go back to SMP. I need to build. What? Oh, I didn't save. I did save. Oh, it can be single threaded, of course. Wait, was it saying you're holding it wrong? Yeah, you're holding it wrong. I don't know. What else can we try? We don't really have a lot of other things that we can try. This is kind of it. So maybe the simple implementation is just slightly more efficient. I suspect that this has to do with the fact that I'm creating slices in some situations where they're not. Although there's also another thing that we should test, I think. We're doing the second test where we are doing a second run, but I'm using get or put in all of those, and they're using a different function, which I think it's roughly comparable. But out of curiosity, what if we didn't do the second run? So we only do the first run. What now? Yeah, there's still a small difference, but it's not huge. So it seems to me that the biggest difference was in the second one. I was still reusing the original function while they were using a different one. And once you remove that, it turns out that it's much more compatible. Interesting. Interesting. So it's pretty much the same. Well, what can I say? So do we leave the README as is? And let's do the backstart issue. Yeah, this is basically to-dos. Yeah, this is interesting though. With this is an inefficient resize because we are copying data over and then we're not we're copying it over and then we're not really um caring that the old data is getting saved. That's kind of bad. No, I'm just gonna say init. Okay, so this is it. Thank you all, and I'll see you next time with probably some more parser work, I think. Let me see what people are doing on Twitch and stuff. Where's Zig stuff? Lucas develops. You know what? I'm gonna read Lucas develops. Go say hi for me.